We are your lungs. We love to keep your body going. We provide the oxygen to fuel your cells so they keep flowing. We're your lungs. Part of the respiratory system. You can find us in your chest.
Okay, this is Chapter 17, the mechanics of breathing. In this chapter, there's a fair amount of background information given in section 17.2 that goes over the gas laws and reminds students about partial pressures. I'm not going to test over that, but it is good information to maybe look over to understand some of the mechanics of breathing. We've moved into the respiratory system, finished up the cardiovascular system. Now we've moved into the respiratory system, and primarily when we think of the respiratory system, we think about gas exchange and bringing in oxygen from the atmosphere and supplying that to the blood. And that's the primary function of the respiratory system. However, there's other functions as well. So one of the most important functions of the respiratory system is the regulation of the body's pH. That regulation is overseen by the blood either retaining or excreting CO2, and that excretion comes about through ventilation and how adequately we're ventilating, whether we have a shallow ventilation or a full ventilation. So there's a considerable amount of a pH balance that goes on in our respiratory system. Additionally, there is protection that is supplied by the respiratory system that protects the body from inhaled pathogens and other irritating substances. So our respiratory system is one of the few systems that actually connects to the external environment. And just like all other systems that have contact with the external environment, like our skin, the epidermis, there's a need to provide pathogen barriers, and this occurs in the respiratory system as well. And then lastly, there's the byproduct of vocalization that occurs through the respiratory system. So the fact that you guys can sit and listen to this lecture, that's possible by utilization of our respiratory system. One of the first things that we have to talk about is ventilation. So what exactly is ventilation? Well, ventilation is the exchange of air between the atmosphere and the lungs. And it takes place in two parts. One is what we call inhalation, in which we're moving air into the lungs. And then we have expiration. Sometimes we'll refer to it as exhalation. That's the movement of air out of the lungs. And the purpose of this external respiration and bringing air in and out is so that we can have that gas exchange that occurs in the actual lungs. So here's where we have the ventilation, in which we have oxygen moving into the alveoli of our lungs, and we have that gas exchange between the blood and the alveoli. When we talk about the mechanics of breathing, we bring in both ventilation, then we go that exchange that takes place at the alveolar membrane, so that exchange of O2 and CO2 with the blood, the transport of then those gases, both dissolved and bound gases, through our pulmonary and systemic circulatory systems, and then finally the gas exchange that would occur in the cell membranes of those target tissues with their capillary blood. So there's these three parts. There's the ventilation part, the exchange of lung to blood, transport, and then exchange of blood to cells. Before we go further, let's kind of talk about the respiratory system and kind of go over the anatomical structures of it and the divisions. So our respiratory system is divided into two parts. One is what we call the upper respiratory system, and the second is the lower respiratory system. The upper respiratory system is made up of our nasal cavity, our mouth, right? We move then into the pharynx at the back of the nasal cavity, and moving down towards the larynx. Okay, the larynx then will move into what the part that we then call our lower respiratory system, in which now we move into the trachea, the two bronchial branches. So we have our bronchi that then go into the bronchioles, and then we finally would terminate in the whether we're on the right or the left bronchus, we terminate into the alveoli. The lungs itself are made up of what we call different lobes. Again, we have an apex at the top, base. So this is kind of the reverse of our heart, right? Where the base is at the top, the apex is at the bottom. On the right side, we'll have 3 lobes. So superior lobe, middle lobe, inferior lobe. And on the left side, we just have 2 lobes. The reason why we have 2 is because this is where the heart will sit, and so it takes up some space as well on the left side in that cardiac notch. Now, I'm not going to test over whether you know superior, middle, inferior. That's for your anatomy class. What I will test on, though, is the distinction between upper respiratory and lower respiratory systems, and what we find in those 2 systems, right? The upper ends at the larynx, the lower begins with the trachea, goes to the 2 primary bronchi, and then into the right, left bronchus, bronchioles, and alveoli. What purposes do the upper respiratory airway serve? So all this part up here, what purpose does it serve? Why do we have this other than to direct air into the lower part? Are there other functions that the upper respiratory system serves? And yes, one of the primary functions of that upper respiratory system is to condition the air. So we condition the air in 3 ways. First, we're going to warm that air up to body temperature. Any of you that have been out in the winter, you inhale really cold air, you feel that burn sometimes in your lungs because you're not giving it adequate amount of time to warm that air. It's important to warm the air to roughly body temperature to protect the alveoli, those cells down at the bottom, where we have the gas exchange, from tissue damage. Is breathing through the mouth the same as your nose? No, right? If you breathe through your nose, there's going to be more warming that occurs than if you breathe straight through your mouth. If you don't believe this, just test this out. The next time you are outside in really, really cold weather, you walk into the freezer section of the grocery store, put your head in the freezer, inhale through your nose versus inhale through your mouth. In the mouth, you're going to get more of that burning sensation. Second thing they do is that we add water vapor to that air. It's important that the alveoli don't dry out. Our body is primarily made up of water. So when we inhale air, we humidify that by adding moisture that's being secreted by those cells in the upper respiratory tract to get that air to 100% humidity. That is the ideal environment for the alveoli to remain in. Finally, the last function they do is they're going to filter out foreign material. So in our nasal passages, in the larynx, we have special ciliated epithelial cells. They secrete a saline-type solution, and we have globlet cells that secrete mucus, and these filter out foreign materials that may be in the air, both particulates and pathogens like bacteria and viruses. The globlet cells, in addition to secreting mucus, they also secrete what we call immunoglobulins, and these are this is a secretion of the immune system that renders bacteria, and in some cases even viruses, it can help deactivate and kind of bind up to where they aren't functional. So that's the upper respiratory system. Now let's talk about how air moves through our respiratory system. The respiratory system functions on what we call bulk flow. And what we mean by that is that we're going to have, due to pressure differentials, we're going to move volumes of gas from regions of high pressure to low pressure. And how we generate these pressure gradients is accomplished by our muscular pump. So we'll use our skeletal muscles to create pressure gradients that can then direct that bulk flow. And this is the part in your textbook where we go into a lot more detail, and we talk a lot more about how we have what generates not just this bulk flow, but also the gas laws that direct particle movement and gas diffusion in respiratory systems. And so if you look in your book, I believe it's in section 7.2, there's there's an overview of some of our essential gas laws that may be helpful in understanding this bulk flow and how we move. One thing that I want to bring up, just like when we talk about cardiovascular systems, is this notion of resistance. So there is resistance to bulk flow. So similar to the cardiovascular system where we were generating a fluid pressure that was directing blood flow from high pressure to low pressure, here with the gas, we also have that resistance that is working against that flow. And one way that we can minimize that resistance is by the diameter of the tube that we're pushing that gas through. So the larger the diameter, the less resistance. The smaller, the more resistance. Now, if we think of our lungs as a volume, what we find is that really there are 4 lung volumes that exist within the lung. The first volume is what we would call our residual volume. This is the amount of gas or of air that remains in the lung even after we have forced all the air that we possibly can force out. We will always have a certain amount of residual volume of air that stays in those lungs. On the opposite extreme, if we look at all air that can be fit in our lungs, we would have what we call total lung capacity, or TLC. Okay, so total lung capacity is the total amount of air and volumes that can fit in our lungs. So total lung capacity, we have residual volume, and then we have a couple other volumes we should talk about. So one would be what we call tidal volume. So tidal volume is the volume of air that moves during simple inspiration, expiration. So when we're inhaling and we're exhaling, the amount of air that we bring in a normal breath, not a deep breath, but in a normal breath, that would be our tidal volume. Okay, so with tidal volume, then we have 2 reserve volumes. So we have what's called the inspiratory reserve volume, which would be after a normal inhalation, the amount of additional air that we can inhale into our lungs. That would be the inspiratory reserve volume. And then we have an expiratory reserve volume, or ERV. Right? The expiratory reserve volume is the total amount of air after a normal exhalation. So we breathe out our air normally on a normal breath. And then if we forced as much air as we possibly could, that would be the expiratory reserve volume. And so these are the volumes that I want you to be aware of. We have capacities, which are usually what we call the sums of 2 or more volumes. If we look at our 4 volumes, residual, expiratory reserve volume, tidal volume, inspiratory reserve volume, then our capacities would be our total lung capacity, which is everything, right? That would be the tidal volume, inspiratory reserve volume, expiratory reserve volume, and the residual volume. That would give us total lung capacity. We have what's called vital capacity, and the vital capacity is the amount of air that we can actually utilize. that we can actually move in and out, I should say, not utilize, but we can actually move in and out. So that's going to be basically our tidal volume, our inspiratory reserve volume, and our expiratory reserve volume. So everything except residual volume. You could calculate that by taking total lung capacity minus residual volume and get your vital capacity. We also have what we call the functional residual capacity. The functional residual capacity is going to say, okay, after we do a normal exhalation, right? So we expire as normal. How much volume is still being functionally reserved with air? And that would be the expiratory reserve volume plus the residual volume. You can see that right here. And the inverse of that would be if that's the functional residual capacity, we can also have the inspiratory capacity, which would be the total amount of air that we can inhale after a normal expiration. So at the bottom of our tidal volume, the maximum amount of air that can be inspired into the lungs would be our tidal volume plus our inspiratory reserve volume. So our 4 volumes: residual, expiratory reserve, tidal, and inspiratory reserve volume. And then we have our capacities, which is when we're kind of putting these together to say, what is the inspiratory reserve capacity? What is our vital capacity? Total amount of air that can be moved in and out of the lungs. Our total lung capacity, total amount of air that fills the lungs, including that residual volume. And then just the functional residual capacity that sits in the lungs that we can still probably be utilizing after normal exhalation breath. I could ask you to calculate any of these, right? Here's some normal capacities in males and females. I don't expect you guys to memorize these, but I could give you, say, your inspiratory reserve volume and your vital capacity, and maybe ask you to calculate out the expiratory reserve volume. There'll be some of those questions in your study guide to help you practice these things. Now, in addition to these 4 lung volumes, we also have some additional gas that is stored in what we call the dead space. So this would be in our bronchi, in the trachea. This is all of the gas that's not in the alveoli. And typically for ventilation and lung volumes, we don't calculate dead space. So let's look at this process of ventilation as we're inhaling and exhaling as a function of pressure that is occurring in our lungs. So the first thing that I want to say is that when we have ventilation, right, our ventilation is going to be a function of so airflow will be a function of the difference in pressures and the resistance in our system. Okay, so as we increase resistance, we would expect airflow to decrease. Okay, if we increase pressure differentials, airflow would increase. Okay, so we move air in and out of the lungs based off this air pressure. In order for this to work by bulk flow, that means that the alveolar pressure, so the pressure in our alveoli, the functional units of the lung, must become less than the atmospheric pressure. That way gas would move down. And we accomplish this by utilizing our diaphragm, our external intercostals, and our scalene muscles. So we contract these muscles, and when we contract those muscles, that increases the thoracic volume in our lungs. So here's our diaphragm. This is at rest. And you can see it's kind of pushing on these, it's minimizing the volume. If we contract this, it's going to become tight, and that's going to allow the lungs to expand. Okay, their volume is going to increase. Now, what does that mean? Well, our lungs are encased in a membrane. So what you'll see is here's our lungs, and then we have this sac that exists around our lungs that prevent gas flow from going beyond and leaking out. And this sac is what we call the pleural sac. And you can think about it as like this is almost like a little balloon in our lungs, and we have the second balloon that makes up the pleural sac that extends around it. And so we end up with this cavity of air that is surrounding our lungs. Okay, I shouldn't say necessarily air. It's fluid filled, right? It's filled with cytoplasm, but it surrounds the lung. And what that means is that we can have this different pressure that is being generated. There's a pressure in the alveoli, so the alveolar pressure. There's a pressure in the interpleural cavity. And when we look at these during inspiration, what we see is, okay, alveolar pressure begins at roughly 0, right? So this is in relation to, in this graph, we're in relation to the atmosphere, right? So we're equal with the atmosphere. Now, as we start to inhale, that means the diaphragm contracts, this volume increases. That creates a vacuum. The alveoli in our alveolar pressure goes negative. So during inhalation, we have a negative pressure that builds up. At the peak of inhalation, we'll hit this maximum, and then it starts to go back to the same as the atmosphere. We start to descend back down to roughly 0. Now, if we look in the interpleural pressure, okay, this is the pressure that's being felt inside the sac. When we contract the diaphragm, that's going to become increasingly more negative. Okay, and if we superimpose that with the volume of air that's moving in, we'll see at the beginning of inhalation, we very rapidly start increasing air. We hit this point where now it's not quite as rapid, and we fill the rest of the lungs. At that point, once we filled the lungs, again, in the alveoli versus the atmosphere, that pressure is the same. That's why we're not bringing in any more air. So during expiration, so now when we're exhaling, the diaphragm is going to relax. That's going to push on the lungs, right? And so we have what's called a passive expiration. We don't have to use muscles to force the air out because of the shape of the diaphragm, and our external intercostals kind of squeeze on the lungs naturally at rest. It minimizes the volume, and so we see, again, our pressure is going to go positive now in the alveoli, reaches a maximum, and then it slowly starts to decrease into where it becomes equal with the atmosphere once again. If we look at the interpleural pressure, we'll see again it starts to become more positive. But you'll notice in the interpleural cavity, we never become fully positive. There's always a vacuum, a negative pressure that exists within that interpleural cavity. And of course, if you look at air moving out, we see that it is going to be forced out, and at the time that, again, we hit 0 in our alveolar pressure, we're not able to push any more air out because bulk flow can only work when there's pressure differentials. So this is what's going on, and it's during ventilation, what's happening with the pressures and how that's being driven. And what's interesting in humans is that we have that, because we have that atmospheric pressure in the in that pleural cavity, that ensures that we will always keep our lungs inflated. That because there's this negative pressure, the lungs want to expand into that entire volume. This is the reason why, like, if you got stabbed with a knife, right? If I stabbed through this and broke this, the pleural sac, this lung would instantly collapse and it would shrink down because now that pressure is going to equal the atmosphere, and so the lung would be much smaller. When we have this negative pressure inside here that allows that lung to inflate and naturally on its own, it's going to stay filled. That's why we have that residual volume of air. The residual volume of air is a function of that subatomic pressure in the pleural cavity. Why is that important? Well, that allows us to inhale when we contract our muscles, but exhale passively without using any force to push air out. Now, this is unique in mammals. In other organisms, that's not necessarily the case. Like, for instance, in birds, they have to use positive pressure to move air into the lungs. So they literally have to swallow air and use muscles to force it down into the lung. You may ask yourself, well, that seems, why would we have evolved this negative pressure? Well, on the one hand, it makes breathing a little bit easier. It's a little bit more passive, uses less energy. We have high metabolic demands. So it's important that we have high ventilation. But there is the downside, right? We are susceptible to having a collapsed lung. If you puncture that lung, you're not going to be able to ventilate very well. Hence the evolution of rib cages and the protection of our internal organs to try to minimize that. Now, in the alveoli, there are some characteristics of the alveoli that are incredibly important for gas exchange. First is this concept of a compliance, or the ability of those alveolar cells to stretch. If you have a high compliance, that means you can stretch really easily. If you have a low compliance, that means there's going to need to be a lot more force in order to expand that alveoli. We see this when people develop restrictive lung diseases, like fibrotic lung disease, in people that have inhaled a ton of particulates and kind of scarred up their lung tissue. As they scar up those alveoli, they're not able to expand as easily, and what that's going to mean for ventilation is it's going to be lower. You're not going to be able to bring as much air in because the expansion, those pressures that you can generate, aren't going to be as great. Likewise, in infants, particularly in premature infants, if they haven't developed the ability to produce enough surfactants, which we'll talk about just in a second, that also lowers the compliance, the ability of those alveoli to stretch. So compliance is important for our alveoli, and then elastance. So compliance is the ability to stretch. Elastance would be the opposite, the ability to return to resting volume when the stretching force is released. If we have a reduction in elastance, then again, we're not going to be able to push as much air out of the lung, which is going to decrease gas exchange. An example of where elastance is lost is when someone develops emphysema, in which you have this disease and the elastin fibers in our alveoli become destroyed. And that means that not only do the lungs now exhibit high compliance because they're able to easily stretch now, they have a really low elastance. So just because you can be compliant, that's great that you can stretch out, but if you can't go back, then there's little gas exchange that occurs between ventilations. Like a great example of this would be, again, the difference between inflating a balloon and inflating a plastic bag. You could probably get the same volume in both of them. Certainly the balloon is going to expand. It has more compliance. And so that balloon would expand more, which is great, right? We want to get more in there. But then when we also release, it's also important to get the air out. When you release a balloon, there's a high elastance as well, so that air is going to be moved out pretty easily. Whereas in the plastic bag, that elastance is not nearly as great. So you fill up the plastic bag and then you release it. Some of that air comes out, but not all of it. It's not like it deflates the same ability that a balloon would inflate. Now, I mentioned surfactants. Surfactants, it's an abbreviation for surface acting agents. And surfactants are secreted by our alveoli, and they serve the function of decreasing surface tension found in the fluid in our alveoli. So it is a secretion that's made up of both proteins and phospholipids, and they decrease that surface tension in that fluid, which decreases the resistance to lung stretch. Surface tension is that physical property in which water wants to cling and hold, the water molecules wants to hold on to themselves. And on the one hand, that's not necessarily always a bad thing, but if you can imagine a very small space in which you have a deflated sac, if there's moisture, water in that alveoli, and it's on both sides of the wall, it's going to attract it to itself, and it's going to be more difficult to kind of overcome that attraction to get that initial inflation. Again, an example of this is if you take a balloon, if you dry that balloon out and you blow it up and just push into it, you need a certain amount of pressure to do it. If you get the balloon wet, not with a ton of water, but just a little bit of moisture on the inside, it's more difficult to inflate that balloon. And so in order to decrease the surface tension, we produce these proteins and phospholipids, and you can kind of think of it almost like, you've probably seen it before where you did the classic experiment where you take a bowl of water, you put pepper on top of it, and the pepper kind of sits all over, and then you drop in a little bit of soap, and it pushes it all, it breaks the surface tension, and all the pepper basically like gets pulled to the sides. Same thing is kind of happening here. We reduce that surface tension. So inadequate surfactant concentrations can lead to problems like newborn respiratory distress syndrome, or NERDS. That's really one of the things that they're worried about in premature babies when they arrive, is that are they able to adequately ventilate their lungs because they haven't yet started producing surfactants. Now, I mentioned that airway resistance is going to affect ventilation and airflow. In general, our airway diameter, if we have a wider airway, there's less resistance. So this is the actual equation, right, that talks about how we calculate out resistance, where we start looking at both resistance as a function of this L constant and then the radius. Don't worry, you're not going to have to calculate this, but it's showing us again how the radius is in the denominator, and so that plays a huge role in when we have a large airway, we're going to a large radius, we're going to decrease our resistance. When we have a small radius, that increases the resistance. How can we change the resistance of our airways? Well, we do that through bronchoconstriction and bronchodilation. And bronchoconstriction is accomplished through parasympathetic innervation. So that increases the resistance. When we use the parasympathetic nervous system, we're actually going to cause our bronchi to constrict and become narrower. So the bronchioles will become a little bit tighter, narrower. We increase that resistance. Additionally, that's the nervous reflex control. They're also under reflex or under control by hormones and other chemical compounds. So, for instance, histamine is a bronchoconstrictor. That's why when you have an allergic reaction, if you're allergic to peanuts and you eat peanuts and then your airways start closing up, it's the histamine that's being produced in those pathways as you're swallowing, right? That's going to constrict and make it difficult to breathe. Now, when it comes to bronchodilation, really, bronchodilation is not under direct sympathetic innervation. What I mean by that is that we don't have sympathetic neurons that go to the smooth muscle in our bronchioles that cause dilation. Most of the control of the airway is going to be done by the parasympathetic, and whether we constrict or kind of slows down and relax. So just like how in blood vessels everything was under sympathetic control, most of the bronchodilation and constriction is under parasympathetic control. However, there are beta 2 receptors in the smooth muscle, and they will respond to epinephrine that's being released and circulated by the adrenal cortex. And so the neurohormone epinephrine can additionally relax these muscles. Again, this is the reason why if you're having a severe allergic reaction, you're given an EpiPen, right? The EpiPen injects it, releases epinephrine into the bloodstream. That epinephrine then will bind to these beta 2 receptors and cause a relaxation, a bronchodilation of the vessels. Okay, but just to note, that's a neurohormone binding to receptors. We don't have sympathetic neurons going to these tissues. When we breathe and we're trying to have adequate gas exchange and adequate ventilation, there's this imperative that both the rate of breathing and the depth of breathing are going to play a role in the efficiency of breathing. So if we breathe really shallow and fast, that doesn't necessarily mean that we're going to be putting in or that we're going to be moving a large volume of air into our alveoli. Likewise, just because we take a deep breath, if the rate of breathing is still high, we might not have enough time for gas exchange. So when we talk about the ventilation, so the exchange of atmospheric gas with our blood that occurs in our alveoli, that's really total pulmonary ventilation. So that's going to be a function of both the ventilation rate and the tidal volume. So ventilation rate is how quickly we're bringing air in, and the tidal volume of how much air is actually being pushed into the alveoli. That would be total pulmonary ventilation. But remember, when we're inhaling into the lungs, we're just looking at lung expansion, the amount of air moving through. In a lot of these studies, we use something called a spirometer that measures that air that we inhale, that we exhale. We have to take into account that we have dead space that really exists in these bronchioles that will move air in, but it's really not ever going to have an opportunity to ventilate with our blood. And so if we want a more accurate depiction or more accurate measurement of ventilation, we would look for alveolar ventilation, which is our ventilation rate times the tidal volume minus our dead space. And as we calculate that out, we can then see the efficiency of ventilation that's occurring. And we can regulate the diameters of both the arterioles, so we can have more blood move through when we have, say, high ventilation rates and high tidal volumes, or we can restrict it and have that blood move a little bit slower through so it has more time to ventilate as it goes by the alveoli. So we can do that on the arterial side. We can also do that on the bronchial side, right? So we can constrict or dilate to ensure that we have adequate ventilation. And that's exactly what we see happening in the body. The arterioles and the bronchioles work together to match ventilation with blood flow so that we have maximal gas exchange, maximal ventilation. Now, how do we monitor ventilation? I touched on a couple aspects of this. We could use some devices like a spirometer, and a doctor could have you blow into the spirometer, and we can measure some of these ventilation rates. Another technique that your doctor does at pretty much every time you go and see your primary care physician, they're going to do what we call an Escultation Examination, in which they place the stethoscope on your chest and on your back. Generally, the chest, they're listening more for the heart. But certainly when they put it on the back, they're listening then on the lungs, and they're trying to see, does it sound right? When you inhale, Are there any sounds that are abnormal? And if you had an obstructive lung disease, like say asthma, then as you're inhaling, we would hear that air kind of whistle a little bit as it goes through that narrow passageway. So you can hear that. You can hear that whistling, that wheezing sound that says, hey, something's going on. And that's how you could just from an auscultation, a doctor could tell if you had, say, asthma or emphysema or bronchitis, in which there is a obstruction occurring and that is limiting the ventilation that is occurring in the body. We'll talk a little bit more about this in our next lecture.